Here we have an application that's going to involve differential equations. We got a tank with 1,000 liters of pure water, and brine that contains 0.05 kilograms of salt per liter is entering at 5 liters per minute. Brine that contains 0.04 kilograms of salt per liter is entering at 10 liters per minute. The solution's mixed and then drains from the tank at 15 liters per minute. And the question is how much salt is in the tank after t minutes and then after 1 hour. So we've got these two brine solutions coming in. We've got the water being stirred around, and then we have some water leaving the tank. We don't know how much salt is actually leaving the tank, but we do know it's leaving it at, the liquid's leaving at a rate of 15 liters per minute. So we're going to let y equal salt in kilograms. So when the brine leaves the tank, again, we don't know how many kilograms of salt that is, but whatever it is, it's per 1,000 liters, because however much salt is in the tank, the whole tank holds 1,000 liters, so that concentration is y over 1,000. And it's leaving the tank at a rate of 15 liters per minute. Overall, the rate of change of salt in kilograms is going to be dy dt, that's how the kilograms of salt is changing per minute, is equal to the rate in minus the rate out for kilograms of salt. Rate in is going to be a combination of the two brine solutions coming in. So we have 0.05 kilograms per liter times 5 liters per minute plus 0.04 kilograms per liter times 10 liters per minute. And in both of these cases, the liters divide out, leaving us with kilograms per minute, which is what we kind of should have been expecting. Now the rate out is a little more straightforward. We've got y divided by 1,000 kilograms per liter times 15 liters per minute. And again, those liters are going to divide out. All the units match. The world makes sense. The math here is that dy dt is equal to 0.65 kilograms per minute minus 0.015 kilograms per minute. I don't usually put units in equations. Don't know why I did there. Simplifying some of the arithmetic, or really just changing stuff into fractions and then getting common denominators, will give us that dy dt is 130 minus 3y over 200. That is our separable differential equation, and it will lead us to being able to say that dy divided by 130 minus 3y is equal to dt over 200. Solving this differential equation by using antiderivatives is going to give us that negative 1/3 times the natural log of the absolute value of 130 minus 3y is equal to 1 over 200t plus a constant k. The negative 1/3 as a coefficient of the natural log is coming out because for dy over 130 minus 3y, that denominator 130 minus 3y is du, and so u is negative 3 dt. So we multiply and divide by negative 3, and the rest of the equation I hope makes sense. Since our variable y is wrapped up in a natural log, we're going to do a couple of things. Number one, we're going to clear the fraction, and then we're going to exponentiate both sides. And so 130 minus 3y is equal to e to the negative 3 over 200t plus k. However, look, we multiplied by negative 3 on both sides, so the first k that we have is different from the k that we have now. So I'm going to call the first k k1. Now we have this situation with the exponent where we have a sum, and so I'm going to express that as a product. 130 minus 3y is then going to be equal to k times e to the negative 3 over 200t, where now this k is actually e to the previous k, so now I'm going to call the previous k k2. Totally legit. As long as these are different symbols, we're all good. Finally, to isolate y, we subtract 130, divide by negative 3, and so y equals 130 over 3 minus ke to the negative 3 over 200t. And because we divided by negative 3, that k is changed again, so we'll call the previous one k3. After all that, it'd be nice to know what k is. Looking back at the original problem here, the tank originally contained 1,000 liters of pure water. Therefore, we can introduce an initial condition. Since initially it was pure water, y of 0 is equal to 0. There were no kilograms of salt to begin with. So y of 0 is equal to 130 over 3 minus k e to the something t. E to the 0 is going to be a 1. And that result is equal to 0. That implies that k is equal to that 130 over 3. Since both 130 over 3 and k are 130 over 3, we can express y of t as 130 over 3 times the quantity of 1 minus e to the negative 3 over 200t. Nope, that t is in the exponent. Looking back at what we were originally asked for here, we've got the how much salt is in the tank after t minutes. And then just for reference, also after 1 hour, we have here after t minutes, that equation y of t is 130 over 3 times the quantity of 1 minus e to the negative 3 over 200 times t. As for b, we need y of 60 for 1 hour. How do I know 60 and not 1 for 1 hour? Because our rates originally were given in liters per minute, so our time is in minutes. So y of 60 is of course 130 over 3 times 1 minus e to the negative 180 over 200, and that gives us an approximation of 25.7 kilograms. I guess to be thorough, we should say kilograms of salt after 1 hour.